Okay, so welcome to lecture 5. So lecture 5 entitled Improper Integrals. Okay, so the integrals that we have dealt with so far include finite limits. Okay, these include finite limits. For instance, the integral a to b of x squared dx. Okay, so a is finite, b is finite as well. Or maybe we can just simply say the integral from 1 to 2. Okay, so this is a finite integral. Okay, but for an infinite integral, this is an integral that is in form of that you have infinity as one of the limits, either infinity or minus infinity. Okay, so let's have an example. Let's look at this function. Okay, so this function goes on, and suppose this is our 1, and this is any number t. Okay, we know that the area under a curve is given by the integral. Okay, so this function is y is equals to 1 over x squared. Okay, so we have 2 there, 3, 4, and we say any value t. Therefore, the integral of this function from 1 to 2, let's say from 1 to 2, what is that area? Y is 1 over x squared dx. So this is just 1 to 2, x to the power minus 2 dx. Okay, so thus we have, when we integrate, add a 1 there, you have x minus 1 over minus 1, then the limits are 1 to 2. So this is just minus x minus 1 over x, 1, 2. So the first we have minus 1 over 2 minus 1 over, just 1. Because when you replace there, we just have a 1. So this is the same as minus half plus 1, which is 1 minus. So our answer is half. So for this integral, the area just here from 1 to 2, just from 1 to 2 is half. Okay, we can also find the area from 1 to 3, 1 to 4, but now we want to see what this area will be from 1 to any number t. Okay, therefore the area, let's say area of t, that is the integral from 1 to t of 1 over x squared dx. This is just as we have seen from the other integration, 1 over x, 1 to t. So we replace with t, we're going to have minus 1 over t minus 1, which is the same as 1 minus 1 over t. Okay, so this is the value or the answer that we get when we find the area from 1 to any number t. What we notice here is that we are taking out a fraction from 1. Therefore, this answer is less than what? Less than 1. So 80 is less than 1, no matter how large t is. So we can therefore conclude that the limit of 80 as t goes to infinity is just the limit of t. Okay, we can say this is 1 minus 1 over t. That is the answer that we have found. This limit is going to give us a 1. Remember, when we put infinity there, 1 over infinity, it's a 0. So our limit becomes 1. Okay, we notice here that our limit is finite, which is a number. We can conclude therefore that this is the integral from 1 to infinity of 1 over x squared dx. Okay, and it is equal to 1. Okay, so this of course is an improper integral. Okay, so let us define improper integrals in a standard manner. So what we're saying is that 1, if we have an integral from a to t of f of x dx for every value number of t for all t greater or equal to a, so t is greater than or equal to a, then the integral from a to infinity, okay, of f of x dx is equal to the limit. So we introduce limit wherever we have infinity. So say t goes to infinity, and this now becomes the integral from a to t of f of x dx. Okay, so this is how we replace wherever that we have infinity, we now introduce the limit. Okay, now similarly, if we have an integral t to b of f of x dx for all t less than or equal to b, then the integral from minus infinity to b of f of x dx is just equal to, so wherever there is minus infinity, again we introduce the limit. So say t goes to minus infinity of, now where there was minus infinity we put t, and there be f of x dx. Okay, so this is how we introduce the limits for an improper integral. Now, something that is worth to know or check here, for any of the above situations, if the integral has a finite limit, so by finite limit we mean say 0, 1, half, 3, or just any number, then the integral converges. But if the limit is infinite or it doesn't exist, then the integral is divergent. Okay, so let's have some examples. One, we have to evaluate this one, 1 over x dx, and check whether it converges or diverges. So we have an infinity there, so we have to introduce the limit. Limit as t goes to infinity of what? The integral from 1 to t, 1 over dx, dx. Okay. Remember, integral of 1 over x is just a lim. So it's limit as t goes to infinity of ln x. This is from 1 to 2. Okay, when replacing t, we're going to say it's a limit as t goes to infinity of ln t. Okay, so we have the limit there. Outside minus ln 1. Now ln 1 is 0. So this therefore gives us limit t goes to infinity okay, so that leaves us just with ln t. But when we replace infinity on t, there we get ln of a bigger number being infinity. Therefore, the limit does not exist. Therefore, the limit does not exist. If it doesn't exist, this means that the integral, the improper integral 1 over x dx is divergent. Okay. So here there's something that you need to know. Ln 0, ln 1, 0, ln of a bigger number is equals to infinity. 1 over infinity is just a 0. Okay. E to the power infinity, please just take note of that. So these are some of the stuff that you need to know, the equations. Okay, so the second one, let's evaluate 2 to x squared dx. Okay, so to evaluate this, of course we introduce the limit of t goes to infinity, 2 to t of 1 over x squared dx. Okay, so we have already done such an equation, the integral. Okay, so how t goes to that, and inside we remain with minus 1 over x, as we have seen. We solved this. and we have 2t there. So let us replace now. We have limit as t goes to infinity. When we put in a t, we have minus 1 over t plus 1 over 2, which gives us 0. Remember, 1 over infinity is 0. So 1 over infinity is 0. This gives this part to be 0. So we have 0. So we have 0 minus, plus half, which gives us a half. Therefore, since the limit is finite, the improper integral is convergent. Okay. So you can go on and do example 3. And now we're just going to move to example 4 from the module. It says, for what value values of p is the integral 1 to infinity of x over p dx convergent? Okay, so solution. Here and in the previous example, example 1, we did a similar question. We concluded that 1 that of x over p dx was divergent. So we can conclude that for p equal to 1, the integral is divergent. Okay, so now let's assume that p is not equal to 1. Then, of course, we have our integral from 1 to infinity, 1 over x p dx. So we introduce the limit. T goes to infinity over 1 t 1 over xp dx. Okay, so we have the same limit. T goes to infinity, and there we can just say x to the power minus p dx. Okay, so when we integrate that, we're going to remember this is just x p or minus p plus 1 over minus p plus 1, which is just the same as limit as t goes to infinity of x 1 minus p over 1 minus p. Okay, so just rewriting, t goes to infinity of what? x 1 minus p over 1 minus p. We have from 1 to t. So let us replace now. We have limit as t goes to infinity. While we have x, put t. So this is t 1 minus p over 1 minus p minus 1 over 1 minus p. Okay, so we can take out what is common, which is just the 1 over 1 minus p. What remains there is t 1 minus p minus 1. This can also be written as limit as t goes to infinity of 1 over 1 minus p, and we can swap this so that we have p minus 1. If we get p minus 1, we have 1 minus p, but we want to get p minus 1. That means we take out the minus, and here we have minus 1 plus p, which is the same as minus p minus 1. Okay, so it's the same as t minus p minus 1 minus 1. Since we have a negative there, we can say this is just 1 over t p minus 1 minus 1. Okay, so this is our integral. Now, for what values do we have this converging? So, we take cases. If p is greater than 1, then p minus 1 will also be greater than 0. Okay, p minus 1 will be greater than 0. So we have t raised to a number, but t goes to infinity. Since t goes to infinity, so infinity to infinity raised to a power that is positive will give us a 0. Therefore, we just remain with limit as t goes to infinity of 1 over 1 minus p. In the brackets they'll have 0 minus 1, which is just the same as a minus 1. So since we're going to just remain with a minus 1 there, and when we multiply we're going to have minus 1 over 1 minus p. Okay, but this is just, now you have to remember that actually we're not going to put a limit because our answer does not contain any t. Okay, so therefore we just have minus 1 over p. So this is just the same as minus, there we say minus p minus 1. Okay, so minus and minus will cancel and we'll have a positive 1 over p minus 1. So if p is greater than 0, this is our answer. But look at this answer. P is greater than 0. So it's P is greater than 1. So if it's P greater than 1, then the only value that we can have is the 0, 1, maybe up to whatever number. Therefore, our answer will be a finite our limit will be finite, and we conclude that the integral will converge. Okay, for all values of p greater than 1. Now let's see what happens if p is less than 1. Then p minus 1 is also less than 0. So let's check 1 over t to the power p minus 1. So this is the same as having 1 over t to the power p minus 1. Now this is what? Less than 0, therefore it's a negative number. Okay, so we have 1 over t raised to the power negative any number. Okay, so this is just the same as t to the power any number. Now, since t goes to infinity, okay, since t goes to infinity, then this value t over a also goes to infinity. Therefore, we'll have when we replace, okay, yeah, so we'll have t over a going to infinity. So since we have that whole thing, infinity minus 1 will still give us. Therefore, let's go back. Remember, our answer was this. So what we are saying is that all this is infinity. Okay. So therefore, infinity minus 1 is infinity, because the bigger number when subtracted 1 is still a big number. A big number multiplied by some number still becomes a big number. So our answer there is infinity. Therefore, we would say that the integral 1 over infinity for x to the power p dx is divergent for p less than 1. But remember, from what we started with, it is also divergent for p equal to 1. Therefore, it is divergent for p less or equal to 1. Okay. So we conclude that the integral 1 to infinity of 1 over xp dx is equal to, if p is 1 greater than 1, it will converge. If p is less or equal to 1, then it will diverge. Okay, so this is what is known as the p-test. p-test for improper integrals. Okay, so that is the p-test. It is very important for us to understand and actually know the p-test. Okay, so we now move on to the comparison test. Okay, so sometimes it is difficult to evaluate the improper integrals. Okay, so we use the comparison test. In this test, we compare the integrals. Okay, so comparison test just states that if we have 0 and the function g of x which is less than f of x for x greater than or equal to a, then 1, if integral from a to infinity of f of x dx is convergent, then if this function is convergent, then even the function that is before it, that is so here what we're saying is that if the bigger function is convergent, then the smaller one will also be convergent. So in the second row, still under comparison test, we're saying that if the integral from a to infinity of a smaller function is divergent, then even the integral of the bigger function will also be divergent. Okay, so let's have some examples. The first one, is that we need to check the integral Okay, so you have to compare this integral to any other integrals that are similar. So we can compare this to integral 1 over ex, or also integral 1 over e x squared. Okay, so you try and compare. Now if we compare it to this function, which one will be bigger? The one that we've been given or this function? Now, you can put in any values. Say, okay, for x equal to 1, what do you think? Integral of 1 cubed 1 over ex plus x squared will be equal to integral of 1 over e to the power 1, which is e, plus 1. And the other one, where we have 1 over ex, we just have 1 over e. So this function now becomes actually bigger, okay, but it would be also important to use this function. So if we have 1 over x squared and our x is just 1, then we know it's this integral 1 to infinity of 1. Okay, so the other one has 1 over e plus 1, then the other one has just 1. So this one is actually bigger than that. Okay, so this will be bigger. So let's use now the comparison test. Let's compare which is greater than. We can actually do this. 1 over ex plus x squared is less than 1 over x squared. Now remember from the comparison rule, if this function is convergent, then even the function that is before it is convergent. So let's check. Is this function from 1 to 1 over x squared dx convergent? So this is a bit similar. Remember from the p-test, we said anything of this sort. So this is similar. So here our p is 2, but this function is convergent for p greater than 1. Now our p is 2, therefore this function is convergent. So yes, concluding that 1 it's convergent. Okay, now since our function is convergent, we conclude that even the question, so this implies integral of 1 over ex plus x squared is convergent by the comparison test. Okay, so this is how we conclude. Okay, let's move to the other example. So in example 2, we have to determine whether this integral converges. Okay, so this function 1 over x to the power ex can be compared to 1 over x. It can also be compared to 1 over ex. Okay, now 1 over x, let's check for x equal 1. Let's see how this function are. This one will be 1 over e. Okay, the other one will be 1 over 1, and this one will also be 1 over e. So we actually find that, okay, maybe 1, let's do 2. So we have 2 multiplied by e to the power 2. This will be half, and this will be e to the power 2. Okay, so exponential is 2.71 something. 2.71 something. So we have half. Okay, the smallest here is this one with a bigger denominator. 2e to the power 2 is less than 1 over 2e and less than 1 over 2. Okay. So so that means that 1 over x to the power ex is less than 1 over ex less than 1 over x. Okay, now from the comparison rule, the first one, if this one converges, then that converges as well. Okay, so let's check the convergence of this function. Okay, so it is very important for us to just check the immediate one. Okay, we cannot for divergence, we're saying that the smaller function, if the smaller function diverges, then even the bigger function will diverge. But since our function is the smallest, we have to look at whether this function converges. Integral from 1 to infinity of 1 over e x dx. 1 over infinity e to the power minus x dx. We have an infinity, therefore we can introduce the limit. Limit as t goes to infinity of 1 to t of e minus x dx. Okay, so this is limit t goes to infinity 1 to t. The derivative of e to the power minus x, let me just do it right away. The derivative there is minus e to the power minus x over 1 and t. We replace minus e to the power minus t minus, which gives us a positive, e to the power minus 1, e to the power minus infinity e to the power minus infinity is 0. Therefore, we just remain with e to the power minus 1. Since this has got no t, we leave out the limit as well and just remain with e to the power minus 1. Okay, so e to the power minus 1, this is the finite number because we know e is 2.71 something. So 1 over that 2.71 is actually the answer. Okay, so therefore by the comparison test, we have that the integral that we ask Okay, so we conclude that this integral actually diverges. So please go and do the other examples from the module, and I'm sure you're able to do those. And we're going to end here with lecture 5. Thank you so much.